Okay, today we're going to be going over this worksheet. It's about a titration of a weak acid with a strong base. I'm not sure what this title is about, but so we're doing a weak acid and a strong base. We're going to be applying the Henderson-Hasselbalch equation, and we're going to think about it as an equilibrium. Now, quick reminder. Here is a classic titration curve for a weak acid and a strong base. And it's going to have volume of strong base added in milliliters as the x-axis and pH as the y-axis. Now, I can tell it's an acid in the flask because the pH starts low. I can tell it's a weak acid because I have this hump here where the buffering is happening. Because it's a weak acid and it does an equilibrium with its conjugate base, then both are present as you titrate it at first. As you start to titrate, it drives the equilibrium to the right, and you get weak acid and conjugate both in solution, and they resist dramatic changes to pH. So that as you add the hydroxide, it shifts it to the right and shifts it to the right, which means that it's going to resist a dramatic, quick change in pH until you get close to the equivalence point. And then you've really overwhelmed that weak acid. You've really shifted it as far to the right as possible. And then the pH is going to shoot up as you add the strong sodium hydroxide base. So, ways to recognize this. If it starts low pH and goes to high, you are titrating an acid, of course. If you have this buffering hump here, you're titrating a weak acid. And you would be titrating a weak acid against a strong base. It would look like a big mess if you were titrating a weak acid against a weak base. And we want to know two very important points on this titration curve. The equivalence point is very important. The equivalence point is when you have neutralized all the acid. Now, what does that mean? Sorry, HA and A minus. You've driven this equilibrium to the right, to the right, to the right. You have none of this left. But with a weak acid, it's important to know that at the equivalence point, all the acid is neutralized, but you have all this conjugate base floating around in solution. Conjugate base is still left. Now, a weak acid will have a weak base for its conjugate. So now this weak base is going to go do its own equilibrium, act basic. So for a weak acid, when you've neutralized all the acid, you only have conjugate base left. The pH at the equivalence point should be greater than 7. It should be a little bit basic because of that conjugate base floating around in there. If this was not a weak acid, then its conjugate would not be a weak base, and it would just not care. If it were hydrochloric acid, it would dissociate 100%. Chloride ions would be floating around in the water, and they would do nothing. They would just be spectators. They would just float around in the water. They would not do any sort of equilibrium. Those chloride ions are highly soluble. They're not going to do anything. So if everything was strong, this equivalence point would be at exactly 7. If you have a weak acid, your equivalence point is going to be above 7, a little basic. And then, of course, the reverse is true. If you're titrating a weak base, if you fully titrate it to its equivalence point, you will have a conjugate acid present, and your equivalence point will have a pH below 7. So, this is the equivalence point. And if you know the volume of strong base, I'm going to make up a number, 22 milliliters. Sorry about that. Then you can do the equation that we know. So this is something else that's important to know about the equivalence point. At the equivalence point, is when you can use the titration equation. You can use either MAVA or MBVB to find the moles of H plus. I said H plus for this one because we're doing a weak acid. If it is a monoprotic acid, then you have also just found the moles of the acid. This could be thought of as your initial moles of acid in the chart. In this case, your volumes need to be in liters because your molarities are in moles per liter. So moles per liter times liter equals moles. Again, I don't need both sides of this if I want to know the moles of my acid. Usually you know more about the base. If you're titrating a weak acid and you're adding strong base, you know more about the strong base. You know its molarity, you read it off the bottle. It's a strong base, so its molarity is its molarity, no fooling around. And so I know my molarity of base, volume of base, I put it in liters, and I know my moles of acid. The other really important point on this chart is the half equivalence point. And to get the half equivalence point, you take half of this volume to find it. So this would be like 11 milliliters. After I've added 11 milliliters of strong base, I will be at the half equivalence point. I am not neutralized here. I cannot use my titration equation because I have not perfectly neutralized it, but I can use my Henderson-Hasselbalch equation. Well, I can always use the Henderson-Hasselbalch equation, but right now I can use the Henderson-Hasselbalch equation in a very easy way. What is true at the half equivalence point is that however much acid you have, half of it has been neutralized. When you neutralize half of it shows up as conjugate base. So whatever this is, it equals that. Your molarity of your original weak acid at this point will equal the molarity of the conjugate base that comes out of that equilibrium. Only at the half equivalence point will this fraction equal 1. The log of 1 is 0. So your pH, sorry about that, equals your pKa. So if you know your Ka, you just take the negative log of it, and you can find your pH. If you know your pH, you can undo this using your log properties, and you can find your Ka. Sometimes you're actually given the pKa, which is what is happening in that worksheet.